saying that we are live. I'm just waiting for those thing to load.
Right.
Like I can see, oh, there we go.
Oh, yes. Okay. Ah, yes. Okay. I see it now too. Okay.
What is it called, Michelle?
Let me send the link in the
Saying
YouTube
that we are
channel.
live.
Not the YouTube channel,
For this
the
thing to load.
Right.
channel. Like I can see, oh, there we go.
Oh, yes. Okay.
It's called 2024 Total Solar Eclipse Geomagnetic Watch,
What is it
the
called,
title of the
Michelle?
YouTube video. Let me send the link in the YouTube channel.
Live.
Not the YouTube channel,
For
the
this thing to load.
Right.
channel.
Find out that I should close my YouTube or I'm gonna get an echo.
Yeah, I'm watching the YouTube while looking at the live channel right now, so all the sound is mixed up. I just closed it.
The YouTube channel.
Right. Okay. So I've closed mine. All right. So I'll just start now. I'm Peter Chi, space scientist at UCLA and the principal investigator of the SMART project. Today is the day of the 2024 total solar eclipse. And if the weather permits, a solar eclipse can be seen from everywhere in the contiguous United States. Many people in the path of totality are going to look up to the sun and experience the beauty of this very unusual celestial event. Science teams across the country are also conducting different kinds of observations to understand the space environment during a solar eclipse. We, the SMART team, are doing something different because we are organizing a special campaign to make new and necessary measurements of the magnetic field during the solar eclipse and study how a solar eclipse can impact the space environment. Unlike in most solar eclipse activities, where you can see the moon blocking the sun, the magnetic field is invisible. But it is a fundamental physics quantity that helps us understand the environment of the Earth and in the space above us. Later, you will hear more about how a solar eclipse can affect the ionosphere and possibly the magnetosphere, which is a magnetic bubble surrounding our Earth. Today, when most of us are thinking about watching the sun and the moon together, one unique aspect of this experiment is that you don't need to view the sun. In fact, the experiment can be conducted without a clear sky because we are remotely sensing the phenomena in the ionosphere that is at 100 kilometers above us or even higher. More importantly, we hope that high schools like yours can experience this very special event with us, hoping that seeing a real science experiment in action can inspire young minds in this new era of the space age. And this is really a rare opportunity to do so because we will need to wait 20 years before we have another total solar eclipse in the continental US. Now, before I introduce members of the SMART team, I'd like to say a few words about the SMART project. SMART stands for Surface Magnetic Assessment in Real Time, and it is a ground-based magnetometer network project supported by the National Science Foundation, and it is headquartered at UCLA. In order to do this project, SMART covers most aspects of larger science projects, such as hardware and software, data management, research, and EPO, that is education and public outreach, uh, under a smaller budget that we have. Um, we operate about a dozen science-grade magnetometers in the United States, and most of them are far from the path of totality of today's event. But the SMART project has been very fortunate to have attracted many talented and highly motivated students at UCLA. They designed and built a small and low-cost magnetometer that we call 3-day mag or 3DM, so that we can provide 20 of them to high schools and citizen scientists along the path of totality. So I have worked on ground-based magnetometers for almost 30 years, and I've never seen any magnetometer campaign for solar eclipses like this. We have challenged ourselves to organize this special campaign for the first time, and we invite you to watch the observations with us live. Of course, please bear with us if things are not quite as anticipated, because we are as anxious as you for not knowing what comes next. But I think this is a very special event for everyone. And now I think it's a good time for me to turn the microphone over to Talia, who is our project manager. Now, Talia.
Hello, everyone. My name is Talia Garcia, and I'm a third-year mechanical engineering major here at UCLA. I'd just like to say thank you to everyone for participating in our research. We're so excited today to be watching the solar eclipse and to have you watch it alongside with us and join us in our research. So thank you so much for watching. I am the project manager here of the SMART team. I'm mostly responsible of overseeing the project as a whole, both hardware, software, and EPO. We've been working on this particular campaign for a little over a year now, and we're really excited for it to all culminate into this event. So thank you so much. I'll pass it to Michaela.
Hi, I'm Michaela Van de Heetkamp. I'm also a third-year mechanical engineering student at UCLA, and I am the Solar Eclipse campaign coordinator for the UCLA SMART project. So I'm very excited to be here. I did a lot of the education and public outreach portion for this campaign, and so I'm really excited to see everything come together, like Talia said. And I will pass it to Michelle.
Hello, I'm Michelle. I am a three-year data science student here at UCLA. My main task here at the Smart team is basically working on data processing, as well as some video editing and helping setting up lots of less technical stuff like these, like the current stream we have right now. Super excited to be here with everyone, and again, thank you everyone for joining in.
Okay. Yeah, thank you, Michelle. Yeah, of course, we have more students on the team, but well, I'm sorry, I probably should. Let's go to Justin and Jean.
Hey, so yeah, I'm Justin. I'm currently part of the software team as a software lead, and these past like few months I've been working on, or me and Jean, we've been working on the app to actually display the data in preparation for this live event. And we'll kind of go more into detail with like how the data display works, and then actually show what our website is actually presenting later on.
Yeah, so hi, my name's Gene Kung. I'm also part of the software group, and I'm a second-year computer science and engineering student here at UCLA. And I work with Justin to basically make the web app to ensure that the data coming in from our hardware is displayed on our website.
Okay, thank you all. And Noel, maybe you say a few words about yourself.
Good afternoon. I'm faculty member from Augsburg University, and we've run a number of magnetic field detection systems around the world, including we have a Dartmouth radio receiving system that's just installed last week. We have magnetometers, and I will show you the magnetometers response to the partial solar eclipse here in Minnesota. These are sensitive instruments that can watch for the ionosphere as well as the solar wind changing.
Okay, thank you, Noel. And Professor Noel Pettis is really very important partner of our SMART project. I think we have received a lot of advice from him in terms of the magnetometer software and the operation. So we're very grateful for his participation. Of course, there are many other members on the SMART team, and if I can project a slide to share with you about who they are. So this is a yes, this is our team webpage you can find. So you can see that we have Matilda and Felipe, Evan, Ilona, Ryan, and another Ryan, and Ambu, and we even have a high school intern, Jonathan. But you see that Chris is on this page as well, and I think I can share a video of Chris. Okay, so that's the end of the introduction of our team. Of course, we have partners across the country, and they help us operate science grade or citizen science magnetometers. So then we will see some of them later. But at this moment, I'd like to have Talia to tell us about the citizen science magnetometers and also for high school that we call 3-day mag. Talia.
Hello, everyone. So I'm here to talk to you about an introduction to the 3-day mag. As project manager, I was also very involved in the hardware team. So here we've had a lot of revisions, sorry, on our hardware and enclosure. So how does this work? Well, first we have two major components of the 3-day mag. We have the RM3100 and the Raspberry Pi. So the Raspberry Pi is a geomagnetic sensor that captures the magnetic fields. That's the main science part of our device. This sends data to the Raspberry Pi, which is the main computer of the device. The Raspberry Pi is this top green board, and RM3100 is soldered onto the blue board. The Raspberry Pi collects the data and processes it, and then is the computer that is able to send it out. All of the electronics on the circuit board, on the blue circuit board, were designed and soldered by hand in our UCLA Smart Lab on campus. When we were designing this, we first designed it in programs like Altium and SolidWorks, and then we're able to build this in real life. We took into account many considerations, but overall, we wanted this device to be lightweight, simple to use and orient. You'll see it's actually pretty small. It can fit in the palm of your hand. Our project has other magnetometers that are research grade magnetometers, much higher precision. And those are very bulky, very big. So these we wanted to be able to use to have high schoolers operate and citizen scientists for this solar eclipse campaign. So you'll see our enclosures are very small. The device is very simple. All you have to do when you receive the kit is plug it in and it automatically connects to Wi-Fi. Um, the device wouldn't be possible without the software team either. Team members worked on data collecting scripts using Python to communicate with the Raspberry Pi for things like how often to collect data and how to store it. Software also transfers this data to our website so that we could see the graph moving in real time, which you'll hear from our software team later from Justin and Jean about how this works and how we can see this data live. We're really excited to share this with you. Here's in the lab when we are building all of our 3-day mags and sending them out. This is what it looks like inside your kits. And then finally, we have a completed kit here. You'll see we have a compass and a level on the top of the box. This is to make sure that we orient the box correctly because we found that through testing, the RM3100 picks up different data depending on how it is oriented. And so to keep all of our data uniform, we have you orient your 3-day mag with the compass facing north so that all of our data is the same. So yeah, that's an overview of the 3-day mag.
Yeah, so moving on to the software, as Talia mentioned, I can kind of go over a brief like summary of how we were able to put together the live data display. So I'll kind of talk about the back end while Gene will go more deeply into the front end. So for the back end, basically we're collecting data from not only the 3-day mag stations, but we've also like gotten data from like an array of magnetometers managed by USGS, as well as another array of magnetometers managed by a company called CPI. And these magnetometers span across the entire US. So they'll hopefully be able to show us like the effects of the eclipse, as well as like the proximity to the path of totality on the actual magnetic field readings. So keep in mind that if you look at our website, we're not displaying the raw values. We're actually displaying the first and second derivatives of the data. So to do this, we kind of did some post-processing of the data after we collected it. We basically looked at the past 50 minutes of data, and then we took 5 consecutive 10-minute running averages over this window. And then using those 5 like average values, we were able to calculate like a first and second derivative. And then these windows are updated every minute or so. These like derivative values will update about that frequently too. And you can see more of the like actual math behind the calculations behind these derivatives on the website. I have it at the bottom of the page. And then going, I guess, more into the technical aspects of things, we like kind of consolidate all the data using a publish subscribe broker called MQTT. So this essentially allows like the different magnetometers to transmit data to like one central server, and then any client, which in this case is our backend, that's subscribed to that broker will automatically receive data as it comes in. And then the backend itself is hosted on Google Cloud through like a compute engine virtual machine that we've set up. And then our front end essentially like makes requests to this backend to retrieve that data and display it. And then one more thing is for the USGS and CPI data, we're basically just using their public-facing APIs and making requests to them through our backend to collect that data. But our backend kind of serves to consolidate all that data so that it can serve all of it to the front end in kind of like one centralized place. So now I think Gene can talk more about how the front end works.
Yeah, so I'm going to share my screen here for our actual front end website. So this is the website that we're using as our front end to host all the data that is processed by our backend. And this is a React-based application. And it's also mobile friendly. So feel free to go to this link on your mobile phone and you're going to be able to have that same experience as me, even though I'm on a laptop. But this is just a simple React-based app. There's a little summary of our campaign. And then, as Justin mentioned, we have our 3D mags along the line of totality, as you see here. And these are the green dots, green markers on the map. And then we also have magnetometers from other stations also on our map. And we have 6 maps, and each of them displays when it displays a different data points. So in the first map, we have the x first derivative, which, as Justin mentioned, is calculated through these equations provided by Peter. And we have that for the x first derivative, y first derivative, z first derivative, and then the same with the second derivatives. And then if you actually click on a point, say I want to click here, you can actually view the derivative that we calculated in our backend. And then if we want to go to a certain station along the line of totality, say, for example, we want to go to Oklahoma 2, which is a high school here. We just go to this select and then click on Oklahoma 2. And then we see the actual graphical data displayed on our front end. And this is all obtained from making requests to our backend. And then we can adjust the granularities. So 1 second, 1 minute, 10 minutes, and an hour. And also we can see the specific data along the X, Y, and Z axes. And yeah, that's basically what our front end is displaying right now. Feel free to go to this link to actually see the live data.
Great. And so I can talk a little more about the different stations we have, the different high school stations we have for the 3-day mags in particular. So I'm going to share my screen. Okay, here. Okay, so first we have the different map of stations here. The ones in red are our different 3-day mags that we have sent out. And so most of these are high schools, I think around 12 of them, and then 8 are other participating scientists. And most are pretty centralized on the path of totality here. And so for our participating high schools, we have Riverview High School with Mr. Brown in Arkansas, East Noble High School with Mr. Lipe in Indiana. Mr. Lipe also wanted to mention that their AP Bio class conducts a lot of experiments and data analysis, so they're excited to be participating in this. We have Lisbon Regional School with Miss Jellistron in New Hampshire, Jay Public Schools with Miss Stapleton in Oklahoma, Broken Bow High School with Mr. McGee in Oklahoma. And Mr. McGee also participated in our last solar eclipse observations in October. We have Palacios Independent School District with Miss Remy in Texas, Ozark High School with Miss Highfill in Arkansas, West Washington High School with Mr. Harkness in Indiana, Madison Junior Senior High School with Mr. Bishop in Maine, Red Creek Junior Senior High School with Miss Brewer in New York, and Miss Brewer also sent a picture of the setup they have for our 3-day mags. Upper Kennebec Valley High School with Miss Samuels in Maine, and Andover Central School with Miss Joyce in New York. So all of these schools set up our 3-day mags and were in correspondence with me for a while about getting the proper information to set up the magnetometers, which was a really long process. So it was really exciting to be able to work with all of them. And yeah, we'd like to thank them for their participation.
Right. Yes, and now I'd like to report that now in addition to the high schools that you just heard from Michaela, uh, we are very fortunate to be supported by many space scientists who are helping us in setting up the 3-day mag in areas along the path of totality where we don't have good coverage. So all these important all of these scientists have their their important roles in their work, and they are very busy with their projects. But the fact that they are helping us tells me, I think it's just evidence that of their passion of science experiments. So I think a smart team really appreciate their help. So I'm going to share a video where you can see them see who they are. Uh, I think that they're 8 scientists who are helping us making the measurements using our 3-day mag. Yeah, I think these are all the scientists that we have been very privileged to work with during this special campaign, and then we thank them for their help. And also, we hope that they're enjoying watching solar eclipse at this time. So now I can stop share, and the next. We also have been helped by um, the program officers at NSF, and also other scientists with helping us operate our magnetometers. Um, so first of all, and we have done interviews with them. So I think if um, we can play the recording of Dr. Lisa Winter. Michelle, is that okay for you?
Yeah, of course. Let me quickly share my screen and let's hear a quick interview from Dr. Lisa Winters. Can everyone see this? Cool.
Yes, I can see.
And yeah.
Yeah, don't hear the audio. Person.
Oh, is there no audio for this? Did is anyone else hearing the audio or is it just
No, I don't
No, we
think
don't hear
so.
the audio.
that's weird? Let me just play it directly out loud then.
Okay, so hi. I was wondering if you could tell me about any NSF funded experiments for the upcoming solar eclipse.
Yeah, I'd be happy to. We have a lot of great projects that we're supporting from NSF, including the SMART project. To study the solar corona, though, we have two groups that are doing some really cool things. Dr. Jenna Samra from the Harvard Smithsonian Astrophysical Observatory is chasing the eclipse in the NSF NCAR G5 research aircraft. So she's developed instrumentation with her team to to observe the solar corona during the eclipse in the near infrared. And this will be a really great opportunity to look at how the solar corona and the inner corona is formed, how heating occurs, and how that then translates into driving space weather. So actually, because they're in an aircraft, they get to chase the eclipse and get a little more time of that totality where the sun is completely blocked except for this outer atmosphere called the solar corona. So that's a really great project. And another one is led by Dr. Shadia Habal from the University of Hawaii. She has been kind of the Indiana Jones of solar eclipses. She's chased them all over the world. A couple years ago, she went to Antarctica and built this really cool platform to be able to observe an eclipse on a ship. This time, since it's in the US, she doesn't have to do any kind of shipboard observations, but she has a team of researchers that are going to be located at a couple places along the path of totality in Mexico, in Arkansas, and in Texas. And one of the things they're going to do is they're going to have ground-based telescopes to observe that inner corona in a range of wavelengths to understand how the solar wind gets driven, understand how coronal heating happens. And she also has two other projects. One is a kite-based project where her same instrumentation that she uses on the ground in her telescopes is hoisted up on a kite in case there are clouds. So the idea is just to get above those clouds and get a better view of the solar corona. And she's also funded by NASA, actually, to have a research aircraft flight as well. So she'll be having some instrumentation on a NASA research aircraft as well to observe the corona from the ground, from the air, by kite, and by aircraft.
Thank you so much. And then do you have any past solar eclipse experiences that you can share, or any plans for the upcoming solar eclipse, what you're doing on April 8th?
Yeah, definitely. I think I saw my first solar eclipse when I was a little girl. In grade school, there was a partial solar eclipse, and we didn't have eclipse glasses, I remember, but they told us to look at the shadows, and I thought it was such a cool experience. It definitely got me interested in astronomy and becoming an astronomer. And then I went to see the 2017 solar eclipse, and I got to see the totality and the corona for the first time, and it was amazing. It was so beautiful, and it was also cool just to see your shadow in the middle of the day. You know, it was around noon, and to see what the birds and the animals were doing too, because all the birds basically were going to sleep. They thought it was getting to be sunset again, and then they all came out again as the eclipse was breaking. So that was such a cool experience. I'm hoping that many of us will get that same experience again this time. I'm going to Dallas, Texas, and I'm really hoping to get to see the solar corona again. This time it will be solar maximum. Last time in 2017 it was solar minimum. So that means that the solar corona will be even more interesting to see this time, and I just can't wait.
Great, thank you so much. So those are all the questions I have. I'd just like to say thank you so much. The SMART project is really grateful for all of your support, allowing us to have the hands-on experience for space science in our project. It's been really, really fun. We're very excited for the solar eclipse. And yeah, it's the end of the interview.
Okay, so that was Dr. Lisa Winter, and we yeah thank her for their support and also I think she has very high interest in solar eclipses, and she is coordinating activities between NSF and NASA on this particular solar eclipse event, I believe. Um, Now, next, we will go to Matilda, who is our education and public outreach lead. And Matilda, could you introduce yourself and then share with people about the science involved in this geomagnetic watch?
Hi, of course. So yeah, my name's Matilda and I'm the Education and Public Outreach Lead for SMART, as Peter just said. And I am a student here at UCLA studying astrophysics, and I'm going to be sharing my screen and showing a little infographic about the science behind the solar eclipse and what happens. Let me know if you can see my screen right now.
Yes,
Okay,
I
great.
can see you.
So to start off, normally in our ionosphere, which is the region full of ions, which are charged particles on the region of the atmosphere, there are these things called solar quiet currents. And these are currents that occur are normally there, and they're associated with the daily geomagnetic variations because of the Earth spinning. And these are caused by solar heating and also tidal effects of the sun and the moon. Specifically, they're produced by these charged particles in the ionosphere moving around, which induce these currents, and they're usually quite not very strong, so on the order of tens of nanoteslas. So what happens during a solar eclipse is that the moon comes in between the way of the sun and the earth, and so due to this, the solar radiation is obstructed, and this causes those ions, those charged particles in the ionosphere, to come together again with the electrons in something called recombination. And this actually means that there's less ions, so this will drop the electrical conductivity of the ionosphere. And according to a paper by Belrose from 1972, this electrical conductivity can decrease to 1/3 of its normal value in the specific blue E region of the ionosphere during a solar eclipse, so it's very significant. So what this does to the solar quiet current system that is normally there is that there will be an abrupt geomagnetic variation because of this. So the obstruction will cause more currents to be induced, and these will in turn affect the magnetic field of the ionosphere and here on Earth. So these currents are strongest near the equator, and you can see a little drawing of them over here. And there's also these things called field-aligned currents that we don't know a lot about, but so these usually avoid the central region of the eclipse, as you can see here. I don't know if you can see my pointer, but in this other diagram here. And so an important thing to note about this effect of the eclipse caused by the moon shadow is that it's an effect that's transient, which means that it doesn't stay for very long. So essentially, it takes some time, and there's a delay in the time that the moon shadow casts on Earth and that the ionosphere actually reacts to this and the conductivity drops. And so what happens is that by the time that this reaction occurs, the moon shadow has actually probably shifted to the next position. So there's never a new equilibrium to be reached, and soon after things go back to normal once the moon shadow has passed. And yeah, so that's what happens. So in the specific place after the moon shadow is cast, the electrical conductivity decreases, and then it moves away from that place, going on to a different place, and then all the SQ current system goes back to normal. As now the solar radiation is obstructed and ionization can happen again. And this effect of the solar eclipse on the geomagnetic field can be up to 40% of its normal value. And this is what we're trying to measure through ground magnetometers here on Earth through the 3D mag network that we have set up.
Okay, thank you, Matilda. And so this is the reason why we're doing this geomagnetic watch. And also the reason why we sent 20 units of 3D max to different places along the path of totality. In addition, and we're studying these data together with the data collected by other magnetometer networks like USGS and MaxStar. And MaxStar is also supported by NSF. So now we go to the software group so that they can show us what the current status of geomagnetic field perturbations are like. So Justin or Gene?
Yeah, so I can share my screen with the website pulled up. 1 second. Okay. Yeah, so we can see here, so out of the stations or the 3D mag stations that are active right now, we can see that um like some of the ones like along the path of the eclipse, um they seem to be having like pretty high readings right now. I'm not sure if I'm like the most qualified to like give an analysis of um like what the all the data indicates. But yeah, if you guys like go to this URL, you guys can like click on each of the individual stations and see how like the first derivatives and second derivatives are changing as the eclipse progresses. Um, and yeah, you can see here like this station just updated. And then also, yeah, one thing we didn't mention before was like the color corresponds to kind of a heat map, where like um colors closer to blue kind of indicate like a low or negative magnetic field reading, and then um colors closer to red indicate like a higher reading. So um yeah, and then these are the first derivative values, and then we look here at the second derivative values. The color coding is similar, but you can see now that the when you click on the actual station, it displays the second derivative.
Now I can, uh, provide some input to, understanding these graphs. Yeah, first of all, Justin, if you can scroll down to the bottom of the page, I think there is a diagram showing that we are using the past 15 minutes of data to derive these quantities. So I think the reason is that the anticipated signature of the eclipse in geomagnetic data will be a perturbation, uh, likely a bell-shaped perturbation in data that can last between 30 minutes to 1 hour. So, and also, I think the effect that this effect is associated with the change in the atmosphere. So now the like what Matilda has said earlier about the change in the atmosphere, there's a recombination charged particles when the eclipse happened, but that recombination may take some time. So I think that has been observed. So there can be a delay in the ionosphere between the beginning of the shadow that the ionosphere experiences and also the reduction in ionospheric conductivity or in currents. So we are looking at the data in the past 50 minutes to allow for the identification of a bell-shaped signature in the last half an hour to 1 hour. So so you're seeing an effect that is during that interval. So if I'm looking at my clock right now, so I suspect that we have, Texas has seen the peak of total solar eclipse if I guess it right. So what is going to happen during today's event is that the eclipse signature will be seen from Texas, starting from Texas and going all the way to northeast. And that would last for about an hour. So we're seeing, for example, the blue dots. Whenever I see blue and red dots, that means that the stations experience stronger perturbation. And you see, for example, like the second derivative, this is very interesting to me because okay, we are seeing like strong signals. For example, you see two dots is that in Oklahoma or next state to it. But I think there are some green dots on this map along the path of totality that may be due to the fact that we're not getting the real-time data. So that whenever you see zero, that most likely that means that we actually are not getting data due to internet issues. But now the fact that you are seeing two red dots close to path of totality during the past 50 minutes in Oklahoma, that suggests, and there's the yellow dot closer to Texas. It could be that the peak of solar eclipse passed through Texas and is now in Oklahoma. But more importantly, of course, I think we're just reading the results from just a few point measurements. But more importantly, Justin, do you think some of the data from USGS and DAISY, that is Maxstar, are coming in this? It seems like they are, you have this light blue dots that suggest to me that they are real data coming in, right?
Yeah, so the circles like surrounded by red are like the USGS stations, and then the circles surrounded by blue are the Maxstar stations. So yeah, these should be like we can look at the values for these two. But I guess yeah, a lot of these stations are like further away from the path of totality, but there are a few stations here that are like closer. And
Yeah. Okay. So clearly, to me that there is a difference between the the results along the path totality and the locations outside of that. And also even along the path of totality, we see negative values and positive values too. So we're seeing both types of results. It is actually consistent with what Matilda just showed, that when there is a shadow on the ionosphere, where the conductivity is reduced. Now you're getting different results on opposite sides of that shaded area. So I would think this is, even though we will have to go into more careful analysis after the event today, but I think this is kind of interesting and not necessarily you know against what we were thinking about, that what might happen. So it's just telling us that it's very important, like what we believed before this campaign, that it is important to place magnetometers very close to the path of totality, so that we can capture these results. Okay, so I think this is, yeah, so there's also, this is very the very first time that, like I mentioned earlier, that there is a geomagnetic watch during solar eclipses in real time. So we're seeing this for the first time by ourselves. So of course, all the interpretation so far, it's very preliminary. I think we'll definitely want to present the results after, at the science conferences afterward. But at least I think it's very exciting for us to see the results. And another point I'd like to bring up is that the results of what we can see today is really not only by what we have produced, but also by made possible by the these other ground-based magnetometer networks. Uh, you know, so they have a continuous operation of science-grade magnetometers, as well as our science-grade magnetometers in the United States. So it is important to maintain and the continuation of the operation, so that we will be able to do this kind of real-time campaign, and also the future observations of other space weather events. So I like to acknowledge the importance of the other arrays in what we are doing. Okay, so that let's come back to these maps after our next part of the Geomagnetic Watch event today, and we have more interviews that we can share with you. So that I think the next one will be the interview with Dr. Charlie Huang. Michelle, could you play that video for us?
Yeah, of course. All right, let's see it. Another interview video right here with Dr.
Um, Hi, I am Jialing Huang from National Science Foundation. I'm a program director in Geospace Cluster. So I want to share my story of my first solar eclipse. It happened in 1989 when I was still a little girl. My teacher say, well, the sky dog is gonna eat up the sun today. And to avoid any kind of bad luck, we're gonna stay in the classroom, close the doors and windows, and hide underneath the desk. Back then, people did not really understand that this type of nature phenomenon, especially in a small town where I grew up. But it intrigued my interest to the sky, everything in the sky, the sun, the moon, and the stars, and inspired my pursuit to a career in space physics. I came to the US for graduate school, had a lot of training, education, and research experience in several universities. And now I'm working at NSF as a program director. We're at the frontier of the most cutting-edge research. We support creative, original, and transformative work. Also, education and outreach. For example, for this Eclipse event, we are hosting several viewing events, including one at Cotton Bowl Stadium. And we're also funding over a dozen Eclipse-related research, like the UCLA SMART project, which will be investigating the ground magnetic field variation and better understand the Sun-Earth system with lots of student involvement. So now it's 2024. Next Monday, I will take my two boys to view the solar eclipse. And we will not hide under the desk again when the Mother Nature does its amazing display. Thank you. That's it.
Yeah, we thank Dr. Huang for sharing her very special experience with us. That is very interesting. And of course, we know about the traditional view of solar eclipses. Actually, at least like hundreds of years ago, that's what it's always something that could scare people. So it's quite natural. But nowadays there's just so much interesting stories about solar eclipses that that you can find and you can think of that makes this phenomena so interesting. So that there are eclipse chasers going after all the total solar eclipses in the world whenever they have a chance. But today, of course, we're at UCLA. We had a little chance of viewing the solar eclipse as a partial eclipse before our live event today, and also we this time we were more interested in the geomagnetic field that is kind of different from many other experiments. But it's we are really excited to share with you this result that what we just saw one earlier, and I think now we can. I don't know how many minutes have passed. If maybe the map have changed a little bit, Justin.
Yeah, I can pull it up again. Let's see. Okay.
No, I think I see one more red dot that was not there earlier.
Yeah, I think maybe the Arkansas one.
Yeah, so it is okay. Oh, that's interesting. I think this might have.
And also, like, one thing to note, I think the y-axis is the one that's like facing into the ground. So I think that one, or like the y value, is probably less meaningful um than like the x and z, which are like the ones that are actually like parallel to the surface of the Earth.
Yeah, okay, so normally I think I hope that we get this right. Normally more in at least in USGS and DAISY data, that is Maxstar, I think they use Y for the eastward component and Z for downward. So
Okay.
I hope that we want to double check that we get that or the same orientation in our 3-day mag. So both X and Y are the horizontal components. Previously, I wasn't sure about the impact in the Z component, but I think it could be the same as in X and Y component where we might see a similar strength in the magnetic field perturbation.
Okay, yeah. So I think like yeah, if we look at our time series graph, like the blue value, which is like the y-axis, is like the smallest value. So I would assume like that would be the one like facing into the ground for us, right? Or like downwards. And then like these values in like the thousands would be like the ones that are actually parallel. So it might be like switched for the 3-day map. Or unless I don't know if I'm like interpreting the values correctly. Um,
Okay. Now, if you can, now it seems like that is a time series data. Okay.
yeah, so we can like scroll through as we can look at the second derivatives. Okay. Yeah, it seems like there's like more red values now, like further north, like
Right.
along the path of totality.
Yeah, it is. Yeah, I see differences from the first set of graphs that you showed earlier. So, and they're perhaps the hotspots, if I can say that, hotspots move a little northward along the path of totality. So, yeah, it seems like that may be what the plot suggests. But there are a little, now if you look at this, okay, let me perhaps share one thing that is because I'm seeing that on these plots, you always see some activity in the northeast, right? Now, so I must say that even though we think that this SQ current might be the dominant currents on the ionosphere, but there are other types of ionospheric currents, especially there are currents at higher latitudes. So if we go north, usually the signatures are usually stronger, and you see the currents may be stronger also because it's getting closer and closer to the auroral zone. And that's just the nature of the geospace. So let's see, if we're getting some hotspots in the northeast that could be eclipse induced signatures, or it could be something else. So we have to keep this in mind that there might be some other activities uh, that could appear in our data. So we will have to check that, for example, if the solar wind is very turbulent during this solar event, for example, our ground stations are gonna pick up as signals too. But no, so there may be some localized processes like the auroral zone currents, so that you always see strong signatures in the north. So both things can happen. So this is something that we're gonna study with other types of data to understand more details. Yeah, but this is definitely something that the results seem to be different from the last set. So that's interesting. So that's we can go to the next video that we have for Professor Noel Petty. So
Yeah, of course. Let's switch it to here.
Good evening. My name is Noel Pettit. I've been on the faculty at Augsburg University at Augsburg College for a number of years, where we studied the magnetic field effects on the surface of the Earth of space weather. There's a large magnetic field surrounding the Earth, and that magnetic field is perturbed by particles flying off the sun and heading in our way, and the fact that we're in an orbit in motion around the sun. We can monitor those magnetic fields and the effects of the sun in space. However, that's very expensive because you have to have satellites. So we have done the next best thing, which is build ground-based magnetometers from the Arctic to the Antarctic. These are magnetic field sensors that are very sensitive. They can detect 1 part in, maybe 5,000, 10,000 change in the Earth's magnetic field. We don't really care about the Earth's magnetic field itself. We care about the changes. So those instruments measure the effect, the fluctuations of the magnetic field, primarily due to solar storms. Solar wind, that is the particles flying off the sun, change from day to day and from hour to hour. What we're trying to do with the smart technology is get that sensors down in cost and availability, so everyone can read the magnetic field. You have magnetic sensors all around you. You have compasses in your car, in your cell phone. Those are not very sensitive to the small changes that we are trying to detect. So most of our detectors, most of our magnetometers are buried in the ground so that they don't wiggle with the wind, and they measure the field changes on a day-to-day, maybe every minute or something like that. So what we're hoping to do with the solar eclipse, when the moon stands in the way, that's going to block some of the magnetic influences of the polar wind. And so we will see a gradual change over maybe a half hour, 45 minutes of the magnetic field down on the Earth, because the solar wind is being blocked, and then it will return to normal. Then it will return to normal characteristics. The magnetic fields of the Earth changes quite a bit on a daily basis. When we are facing the sun, then we're bombarded by those particles, and the magnetic field is compressed on the sun side, and it expands on the dark side, on the evening side. And so we expect to see somewhat situation like that, but only in maybe a half an hour time frame. The detectors we use are very inexpensive, and we hope to generate some interest in the storms that are going on at the magnetic field, as well as the other phenomena that affect the ionosphere and the magnetic fields of the Earth.
Okay, yeah, we thank Professor Noel Pettit for sharing his experience in ground-based experiments. So now I think we are. I was checking where the peak of solar eclipse is right now, and I think now we're about 3:50 Eastern time. So I think the peak is actually in the northeast already, but because we are studying the the data in the past 50 minutes, so I think that perhaps we're we're seeing the results, associated with, the eclipse in, lower latitude. But maybe it's another time to go to Justin's, a plot in, that made by the software group and seeing what is the status right now. Okay. So I think, I remember, if I remember right, the peak of the eclipse, especially the total solar eclipse, will go from Texas to Vermont or Maine, maybe Maine, in about an hour. So I think this is probably, the peak is right now probably in Maine already. So if we look at the 50 minutes before that, so it seems to be, perhaps it will be in the middle of the shaded area. So we are seeing some stronger values here. So okay, so that's yeah. Still strong values in Arkansas and Oklahoma. But the opposite, there's some like a close. No. So what this set of plots seem to show that there could be some very opposite values. Like you see, blue colors and red colors close to each other. So we're gonna study what that means. So, but that is possible because I think, we're sensing this uh ionospheric currents that, or even magnetospheric electric currents that could produce different polarities on the ground. So we just need to look at more signatures or more data after the event. But you're seeing now in this diagram, maybe let's go to second derivative. Okay, so it seems like it's in the middle of the path, but of course there's a opposite value in the northeast. So again, we'll have to check the solar wind and magnetospheric activities to understand whether or not there's some high latitude perturbations that is not caused by solar eclipse. So it seems like, okay, we are seeing, okay, this seems to be less values in the Z component. Okay. So of course, eventually when we gather all the data, we're gonna study the magnetic field orientation in 3D and also the inferred electric currents in the ionosphere. So okay, thank you, Justin. So I think it may be time to go to the last recorded interview that is by Dr. Christy Vera, Southwest Research Institute.
Yep, let me just share my screen again.
Hi, so my name is Christy Hera, and I'm a scientist here at Southwest Research Institute in Texas. We have a couple locations that do specifically space science, either planetary, astrophysics, or helio, but Southwest Research Institute as a whole does everything from water, deep space, communications, high physics. So it's more than just space, but I am in the space sector. So I get to make instruments and test out
new designs before we propose them, and most of our instruments end up in NASA or the European Space Agency or NOAA, for example. Those are our latest three clients, you can say. And I'm lucky enough to also look at the data once it's already in space and get to do science.
Yeah, perfect. That's so nice. You have all these research and all these instruments testing going on, Dr. Leah.
Yeah.
Can you maybe tell us a little bit more about your research and like what are the most excited parts about your exciting parts about your work? What are you most excited about?
Sure. So I've been trained to do magnetophysics, and I actually been doing solar wind interactions with different small celestial bodies. So that includes the Rosetta mission from ESA, the European Space Agency. I also have worked near our magnetosphere, and I've done stuff called energetic neutral atom. So we have a ring current or charged particle that's surrounding us on Earth, and they go under charge exchange, and as also they follow the field line. So during the North and South Pole and the cusp regions, we have precipitating ions. So I study specifically when they change in between neutrals, how I can image them and get information of the ring current and also magnetosphere in general from that one signal. And in the Rosetta one, it was also how the solar wind was interacting with that weakly magnetic environment, because it wasn't a very active comet 67P. And what I'm really excited is that every few years I can have a completely different shift in my emphasis in the science, but it's the fundamental that really helps me bridge the gaps and more of an expansion into the science. I really like to look outside of where the focus is. Like we could have built an instrument for this mission and this environment, but we can get secondary science that we didn't mean for. So it's how to enrich that data set even more, and then also how that can inspire new techniques to not be grandfathered in and doing the same instruments, but to expand what we know from what we've learned recently. And an example of that is that I'm looking into 3D printing instruments for space. And on that note, there's a lot of new materials coming out there that makes it really exciting, because now they're putting into conductivity aspects into the materials, as well as making sure that they're low outgassing. But since it's a commercial field, they don't really have an eye for space applications as of yet. So my job is to put it in the lab, test it, see how well we can make these materials work for us and for our purposes. So I'll be doing that for a couple months. And I'm also leading students in getting experience in fabricating instruments as undergrads and graduate students, from engineers and also scientists as alike. So that way you're learning how to communicate between the different disciplines and get real hands-on experience. And that project is a sounding rocket and building an ESA, electrostatic analyzer, so we can monitor that in conjunction with another mission that's also looking at the field lines. So,
wow, that's definitely a
it's a lot.
lot of super cool projects going on, a lot of data collection, a lot of new things to learn, new things to push, 3D printing, these all sounds amazing. Yeah, and kind of switching to our more of a main point for today. I know the solar eclipse is coming very soon. How do you think the solar eclipse will affect your research, and what are you the most excited about the solar eclipse?
Well, I'm excited because I'm literally in the path of totality. I live on the far west side of San Antonio, and I will have almost 3 minutes without having to get out of my backyard. And then it's exciting to see a lot of excitement locally, and a lot of schools and after school programs reaching out to us because they are aware that we are in their backyard essentially. So it's been exciting to have that excitement coming up and building up throughout, because we also had the October annular eclipse, and it was pretty close, like the crisscross of the two was practically next to San Antonio. So we've had a very active solar viewing window, and it's been many years since we've had one in Texas, so it's been great. I'm personally excited just because I would like to experience it in real time. Most of my data taking techniques is remote sensing, so it's really nice that I will be able to experience it. One of the most exciting is the fact that it will literally be nighttime for a few moments. And even though we experience that every day, the way that we darken into night takes much longer than it will be during this eclipse. It would be very rapid, so you can literally hear the effects of that on the animals. The animals will go into their defaults of like, oh, it's nighttime, and it can be a minute of transition, and they'll nocturnal come to life and everything like that. So that would be exciting to experience. And what else was part of the question? Because I got excited.
That's pretty much it. I'm just asking, like, what's the most exciting part you think about the solar eclipse? And it's super nice to hear that you're right on the solar eclipse line. I'm super jealous myself. Kind of as working as a data processing student, all I can see is remote data, like people are looking at stars, people are looking at stuff. So I'm here staring at the numbers. But yeah, it's really nice that you'll get to experience at least like a few minutes of it. Yeah.
But no need to be jealous. I could be covered in clouds, so I might need equipment just to see it, or get the news of it throughout the day and then see it from other people's perspectives as they like bring it up into social media or the news outlets. So that'll be good. But I'm also really excited because although I am one of the sites for the SMART, I'm the site 10. I just received this just like a day ago. So I'm waiting to get the manual so I can make sure that it is installed properly in time to have this data point as well as the one that we have here on site. So I'm excited to actually be able to have some hands-on time for this eclipse.
Yes, yeah. We thank Christis for sharing his passion about science projects and also this particular solar eclipse, where we hope that she already witnessed the total solar eclipse in San Antonio. So I think we can, if maybe we just spend another minute going back to the maps again before we end today's program. So, Justin, could you show that again to us?
Yeah, so I was actually looking at the time series data, and this is for like a station in I think in Arkansas. But you can actually see like this is like the x-axis magnetometer data, but you can see the value or the reading like there's like a clear kind of dip as I'm assuming this would be like around it's like between 12 and 12:30. So that's like around when the eclipse like passed over
Yes,
Arkansas
I
maybe.
would think so. Yeah.
Yeah, but you can see there's like a clear like kind of like bell curve almost like as the eclipse progressed. So I think like yeah, if you guys like look at the time series data, it might be um easier to like visualize some of these. And then same thing for like the z-axis data. Like you can see it dips like around the same time periods. So that could be like an indication of like the effects of the solar eclipse. But yeah, we can go back to the map. Wait for
Right. So we anticipated that we were going to see something like this. The bell-shaped curve could be like concave or convex. Depending on where it's located with respect to the change in the atmospheric current. Because I think we all know that electric currents will induce magnetic field surrounding it. So we're actually studying this using this very same physics principle. and just interesting that the sun or the eclipse could induce that signature on the ground. And now we're seeing, okay, so this is right now. So I think there's still very strong signatures in the north. Of course, we were only a few minutes from the last set of plots, so we're not too far away. But I think we're still seeing some activities in the central U.S. But it may be possible that we will only be able to see more changes in the Northeast, after today's live program, because we need to collect about 50 minutes of data to show the results. But I think, but Justin, is that the your front end will continue to operate, and whenever it's getting data?
Yeah, and the data should still be like coming into the back end. And I forgot to mention this earlier, but we're also storing the data into like a database. So if we need to do like further analysis on it later, it should be easy to retrieve. But this front end should be like I can leave it up as long as we need to. So
Okay. Okay, this is very interesting. Okay, so now, now we're seeing, if we look at, for the first plot for the first derivative in X, we now see some red values at some of the USGS stations, or DAISY. Maybe those are DAISY stations.
yeah, I think those are the DAISY stations.
Okay, so see, so they are picking up some signatures on their end. So okay, that is interesting. Because of course I have to say that now our 3-day max are very simple systems, but their magnetometers are really the science grade magnetometers. So is which station are we looking at?
This is Indiana, I think.
Oh, okay. Still
I'm just seeing if there's like any patterns here.
Okay, so we definitely will study more. I mean, so we're definitely seeing some data coming in real time. I can say that it's kind of a rare experience for me. Also, even I've worked on this field for many years, but being able to see this kind of real-time maps is really a quite an experience. But definitely, with the work by you guys, I hope to see this more and more. And but then we really see the power of network observations when we put all the data together. Um, now, I think we're at the end of the program today. So before we close, I wonder if any of you want to share some reflections, or you have anything to share with people.
I think this project has come a long way since it was first thought up last year, and I've been able to be a part of it the whole time and see all of the revisions, all of the preliminary ideas that we have had for this project. Yeah, it's definitely been through a lot, and there's been a lot of problem solving involved. We learned from what we did last time in the October eclipse, and now we're able to do it better for this one. And we just, again, I want to thank everyone on the project for all of their hard work. This was a lot of hard work from these undergrad students, so thank you everyone in all groups, and especially thank you to our PI, Dr. Peter Chi. So thank you so much.
Yeah, and it's actually it's my great pleasure to have the opportunity to work with all of you because otherwise my world will probably be just sitting in front of my computer. But of course, I think it's so grateful that I have experience working with all of you. I think everyone, each of you is very different to me. And that's it's a wonderful experience too. So if no more comment or and maybe we will just close the program by saying to our audience that we thank you for joining our Geomagnetic Watch for the 2024 total solar eclipse. And I believe this is the first real-time geomagnetic watch during any solar eclipse. We hope that you like the experience and the adventure with us today, and also the stories shared by the experts that we interviewed. So even though this is the end of our program, but please feel free to reach out to us whenever you want to know more about solar eclipse effects on the geomagnetic field and on the geospace environment. Yeah, thank you so much for your time today, and see you next time. Bye-bye.
Thank you.
Thank you.
Bye.